Hi, everyone, and welcome to this week's lecture. Today, we're going to be covering Chapter 12 of your textbook, or Shooting Scene Documentation and Reconstruction. So, as usual, these are our learning objectives. So, use these as a tool for a study guide, as well as just to gauge your understanding as we go through the lecture itself. So, jumping into shooting scene reconstruction, we have to understand terminology. So, some of the terminology that is important when it comes to shooting scene reconstruction is going to be perforation, or going all the way through an object like a wall, penetration, which is going through maybe that first layer of a wall, but not going through the entirety of the wall, embedding, it's sitting in that first layer of the wall, spalling, it penetrates and then it hits the backside, but it causes the spalling or the breaking apart of pieces on the second half of the wall, but it doesn't perforate or go all the way through. And then deflection, where an object like a bullet will come off and hit the first part of that wall and then deflect or reflect off of that piece of wall. And then, so those are the different type of trajectories and travel paths that a fired projectile can make and what can happen as an end result at the very end of the terminal process. And then before we even can get into firing a bullet or having a fired projectile, we have to understand the anatomy of a cartridge or a complete unfired projectile. So that's the bullet as well as the cartridge case combined together. So in the anatomy of a cartridge, we can see that there is a primer, and the primer is what is struck in order to allow for the bullet or the projectile to travel through the firearm. So we have the primer, we have the cartridge case, which is made of brass. You have your propellant that helps to push that projectile out. The flash hole, where once the primer is struck, it flashes through, igniting the propellant to then push the projectile through your firearm. Then you have lead, which is what your projectile is made of, and then the metal jacket that covers your projectile itself. And then here's just another breakdown of that same type of anatomy of the cartridge itself. So, jumping into shooting reconstruction, trajectory analysis involves three areas of related ballistic study. Each area of study in this is accomplished by different parties, but all are necessary to understand the scene itself. So, the first is going to be interior or internal ballistics, the second is going to be exterior or external ballistics, and the third is going to be terminal ballistics. So when we diagram this out, we can see that internal ballistics is what's happening with the cartridge inside of the firearm itself, what's going on internally. So we can see that the firing pin hits the percussion cap of the cartridge base. The bullet is then going to start traveling through the muzzle of the firearm. And once the bullet exits the muzzle of the firearm, now we are in the external ballistics stage. So then as that bullet travels after exiting the muzzle, up to hitting the target, that is going to be our external ballistics, right? That whole entire path as it travels through the air. And then our terminal ballistics is going to be when it hits the target at the end. So internal ballistics is conducted by the forensic firearm examiner at the crime lab. This involves looking for the function and operation of the weapon, the association of the weapon, and then the bullet in its cartridge cases. So does the weapon actually work? Could it have fired these types of cartridge cases that were left behind at the scene? Who owns this weapon? What's the serial number of this weapon? How many hands has this firearm traveled through? Okay. And then this is often going to involve evaluation of ejection patterns and gunshot residue range determinations. So when it comes to terminal ballistics, this is conducted typically by the forensic pathologist, especially as a person who would be the terminal side of a gunshot wound. So this involves defining the path of the bullet through the body, the associated damage, and differentiating entry from exit wounds to understand where did the bullet come from, where did it enter, where did it leave, did it leave, is it penetrating, is it perforating, and things like that. This also includes issues of range determination. So how far could someone have been standing away from a decedent to fire this firearm? So that way we can get another understanding of what did this scene look like, where was this firearm fired, to understand the internal, external, and then terminal ballistics as well. So when it comes to range determinations, forensic firearm examiners use the weapon and similar ammunition to create gunpowder residue standards at different distances. These are then compared to the questioned residue. So what that means is we have to have a known firearm that we suspect fired these um, projectiles on scene. Okay, so when we have a known standard of that firearm that we believe is our suspect firearm, then we take whatever ammunition that is similar to the ammunition that was fired on scene, and we'll shoot in the crime lab from different distances. So we'll do close contact, we'll do uh, loose contact, we'll do close, we'll do intermediate range, and then we'll do an indeterminate range. So we can understand how the gunshot residue will uh, position itself against a different target so we can get an idea of how that specific firearm allows for the gunshot residue to spread out, smoke out, and then we can compare our range determination standards that we have just now created to the standard or to our questioned at from the scene. So that way we can say, okay, based off of this specific firearm that we have used in this type of ammunition, we can say with a certain level of certainty that the suspect was standing at this distance from the target at the end of the day. So the forensic pathologist defines approximate range by evaluating physical characteristics of the wound, with ranges including close contact, so pressed to the skin, loose contact, so close proximity to the skin, having like a small gap between the actual muzzle of the firearm as well as the skin itself, near contact, not more than 5 inches from the wound. And then we have intermediate range, so that's 5 to 40 inches from the wound. And then we have indeterminate range, where there are no characteristics, so there's no conclusion that we can reach about range determination. So when it comes to external ballistics, this is conducted by the crime scene analyst most often and may involve the firearms examiner. This involves defining the path of a bullet through the scene by evaluating various scene aspects like penetrations, perforations, cartridge cases, and known position of the victim or shooter. So ultimately, it defines possible and impossible scenarios for bullet trajectories. So jumping into bullet defect characteristics, we have entry versus exit hole sizes. So the size of a mark a projectile leaves as on an object is related to the material the object is made of, the shape, size, and material of the projectile, and the projectile's velocity as well as other miscellaneous factors like painted surfaces, wood density, soft body tissue, intermediate targets, glass tempering, and ammunition variations. So when it comes to entrances, we are going to locate where the bullet first enters a target surface, and this is going to be relatively circular in shape. When it comes to paint, you can see a perpendicular angle because of the metal flex, which breaks the bond between the paint, snapping it off. So in this case with a car, you can see that these relatively circular points or locations on the car, that's going to be our entrance. And you can see the paint around it. This is where we are seeing that metal flex breaking the bond with the paint and therefore snapping it off. So that's why we're not seeing any paint around the entrance defects of the car itself. When it comes to something like tires, rubber will close back up, making the defect not very overly obvious unless sufficient air is lost, right? That's because rubber is very elastic. So even though you have caused something to penetrate or perforate through, then it's going to still snap back to its original position as best as it can. So that's why we see a very small circular entrance defect in the tire right here. And then for a 90-degree entry to drywall, bullet wipe with black ring surrounding the defect. That's going to be primer residue, lubricant, lead, carbon, dirt. And those residues present mean that there was no intermediate target. So we have an idea of where we can actually use this for range determination. And because we're seeing all of this stuff and all of this gunk on the wall itself, what we mean by no intermediate target is that there was no person that was standing there. Okay. So if there was a person standing there, if there was like a pillow that was there trying to silence a gunfire, we wouldn't see all of this gunk that's left behind, which is what allows us to perform range determination still in this type of scenario. And then we have exit defects. So generally these have an irregular or asymmetrical shape. It's because the material is going to be pushed out from the defect, suggesting an exit. So it's going to show the direction of fire. So you can see here the material is being pushed out. So the styrofoam is being pushed in the direction of fire that the bullet would have traveled through. And again, you can see the material is being pushed out as the bullet was traveling through or in that specific direction. So then going into angled shot defects. So when we have an angled shot, we have what's something called the leading edge, and that's the portion of the defect produced by the initial contact between the bullet and the target surface, producing a shoulder and or an impression. So here we have our leading edge right here, and that's where our bullet first came in contact with the surface and started traveling in that direction. And then over here again, we have our leading edge, and then the pushing through of the material on the surface, producing um, some more defect along the way, which tells you the path of travel. And then we have also the pinch point. This is a small area of survivable paint that was pinched between the bullet's initial contact point and painted sheet metal surfaces. So here we can see that there's a small pinch point, and you see a piece of paint that is left behind. It's because as that bullet is traveling at such a high velocity, once it comes in contact with the surface, it's creating that friction, and it's all of that heat from that friction is going to preserve that piece of paint at that pinch point. While that initial friction is going to produce all of that heat, it's now losing friction, it's losing velocity, and that's why we're not seeing the preservation of paint as we travel across the surface itself. So some concerns that we have to keep in mind are going to be deflections, tumbling, keyholes, ricochet, and then vehicle flight path. So bullets don't typically travel in a straight line. There are rotational forces that are always in effect that keep the bullet off a straight axis of flight. So we'll see yaw, and that's the rotation of the nose of the bullet away from the line of flight, going up and down and up and down. We have precession, which refers to the rotation of the bullet around the center of mass. And then we have nutation, which refers to the small circular movement at the bullet tip itself. So, right, we're not always seeing that consistent straight line of motion. So yaw and precession decrease as the distance of the bullet from the barrel increases. So the longer it's been traveling, we see less yaw and less precession. So going into deflections, bullets that deflect create distinct defects. The bullet itself may show indications of the angle at which it was deflected. So here we can see the destruction of the bullet. That gives us an idea of how this bullet hit the surface. And then you can also see the striations of the surface characteristics that were imparted on the bullet that tells you the angle at which it hit that surface as well. So going into tumbling, this refers to creating, again, distinct characteristics, eliminating any possibility to evaluate impact angle. So essentially, in this case, our bullet was not traveling in that straight line. It was tumbling as it traveled through. And because it's tumbling, that means we can't evaluate impact angle because we don't know at which the angle impacted, essentially. It didn't travel straight through an object to give us that nice pristine angle that we can then perform trajectory analysis with. So here you can see the actual shape of the bullet as it traveled through each of the surfaces or hit and then deflected off a surface. So going into the keyhole defect, this is damage indicating the bullet has started to exhibit a tumbling action and can be the result of contact with or passing through an intermediate target. So that could be passing through a wall and then hitting the final target. That could be passing through a pillow, hitting the final target. That could be passing through a person and then hitting a wall behind that person. So there are different types of intermediate targets that we might see here that help cause this keyhole defect. So then going into the ricochet defect, this is a change in angle and or direction of a projectile as a result of impact with a substrate. So the angle of ricochet, or the angle of departure or departing projectile as it leaves the substrate. So what we can see here is we have the bullet incoming, spinning normally, and then we see that there's some ricochet. So the nose is now going to bend upwards, and a rear profile is created as it's still traveling. So going into flight paths and vehicles, there's going to be compressed and punched out sections of foam padding, creating the shape and appearance of a French fry almost looking thing. So an intermediate flight path that has perforated or gone through a seat cushion. So when it comes to calculating bullet impact angles, this all goes into trajectory analysis. We first look at the bullet cross-section and defects. So this is going to be very similar to what we'll talk about with bloodstain impact angles as well. So just keeping in mind the similarities in these calculations. So first we're looking at the diameter of any part of the bullet's cross-section. So circular, we have our AB line and our CD line. So AB is equal to CD, right? It's a circle, the diameters are going to be the same. So then when we're looking at the path of travel, we have our bullet traveling at an angle, hitting our target, resulting in a bullet defect, and that is going to cause our impact angle itself. So going for analogy of the defect to a right triangle, we have our opposite hypotenuse and our adjacent, right? So coming back over here, we can see that we have our hypotenuse, opposite, and adjacent, forming our right triangle. And then we remember inverse sine of our impact angle is opposite over hypotenuse, or AB over BC, right? So AB over BC, or our minor axis over our major axis. So when it comes to a bullet defect, we're looking at the oblong or the elliptical shape, and our minor axis is going to be our AB, our major axis is going to be our BC, okay? So when we look at our defect here, we can see that we have an elliptical shape, and then translating that, this portion of our elliptical defect is going to be our minor axis, which makes this portion our major axis. And then we can actually go in and calculate this angle. So our width is going to be our minor axis, our length is going to be our major axis. Let's say our width here is 9 millimeters and our length is 15 millimeters. We're going to calculate the ratio of our width to length. So 9 millimeters over 15 millimeters is 0.6. And then we take the inverse sine of n, because this is our n, and that is going to be our impact angle. So our sine inverse of 0.6 is 37 degrees. So that is the angle at which our bullet in here would have hit our target. All right, just jumping forwards. So one of the ways that we are calculating or looking for trajectory on scene in order to perform shooting scene reconstruction is using trajectory kits. So the primary concern of external ballistics is evaluating those bullet defects. So trajectory kits are used to do this and include rods, centering guides, angle finders, and in some cases lasers. So first, we have to verify that the defect that we're seeing is in fact a bullet hole. So this is done based off of visual examination, presence of bullets, cartridge cases, remnants, and then the chemical presence of lead or copper. So it is very easy to use a trajectory kit. So basically you're going to take one of those rods into a perforating defect, right? So remember, a perforating defect travels through and through. Penetrating is just through one side of like a wall or something like that, and then sits inside of that object. You're going to use centering guides to level the rod in the defect. And then a lack of centering guides can affect the angle significantly, and we want this to be as accurate as possible. The reason we are doing this when we are performing shooting scene reconstruction and looking at trajectory analysis is so we can figure out where our shooter could have been standing. And this is very, very useful, especially when we have for range determinations. If we don't have any stippling or gunshot residue that's left behind on the target, we don't necessarily know where our shooter could have been standing. So trajectory kits and determining the angle at which this shot could have been fired is going to be our best case scenario in order to reconstruct the scene and figure out how things happened. So the centering guides are used on both sides of the perforation, and the guide should not be forced into the defect, but should be held in place by small rubber grommets because we don't want to cause any further defects of our original defect itself. Over any distance then, a laser attachment is used to demonstrate the trajectory. Strings and other items can also be stretched along the trajectory, but these will sag and not be as functional or as precise as a laser. So looking at this in images, here we can see that the rod is inserted into our defect. And then we can see on either side, we have our centering guides, making sure that it's going perforation, right? Traveling through and through. Everything is set, put together. And then we put a laser on the end of our rod. And then that laser is what shines and can point to exactly wherever the person could have been standing, so we can get an idea of the shooting scene reconstruction, where this all could have happened. And in order to illuminate this laser, what you're going to do on scene so you can photograph it, you're going to take something, spray like some spray baby powder, some dry shampoo, and you're going to spray it along the way the laser is, because the laser is going to reflect off of all of those particles. And as you're taking a photo of this, you're using a long shutter, so that way you're allowing for the laser in and of itself in all of its entirety to be illuminated as you're taking that photo. So you can show and demonstrate that reconstruction of the laser and what angle or where that laser travels to indicate where a person could have been. So when it comes to documenting trajectory angles, the trajectory rod represents two basic angles that must be captured and photographed properly. Failing to capture this information may make the trajectory worthless. So the two angles are the angle of elevation and the angle of departure. The angle of elevation is viewed from the side. This is also known as the vertical angle. And then the angle of departure is viewed from above, and this is known as the horizontal angle or the angle of azimuth. So both must be documented and should be photographed. And this is what allows us to do that impact angle calculation. So for our angle of departure or our horizontal angle, again, this is the trajectory as seen from above. So the photo is taken from above. So what angle could the firearm have been held at in order to produce the bullet defect that we see? So in real life with our trajectory kit, going again from above, we can see the rod is coming in this way, and we have our protractor here to give us what that angle is. And then for our angle of elevation or our vertical angle, how was the suspect holding the firearm at what angle to cause that bullet defect? And then in real life, this is going to be, again, where we see our trajectory rod and we hold our protractor off to the side. All right, so that concludes everything to cover for Chapter 12, Shooting Reconstruction. And with that, I hope you guys always know you can reach out to me with any questions you may have, and I will see you in the next one. Bye.